Today's video will deal with an important theorem known as the intermediate value theorem. Suppose we have a continuous function f that is on a closed interval from a to b. We're going to let n be a number between f of a and f of b. F of a and f of b are y values, so therefore n is a y value. So essentially we're saying pick some y value that is in between two other y values. And we're assuming that f of a and f of b, those y values are not equal. So pick a y value in between two non-equal y values. Then there's going to exist a number c in the open interval ab. Now a and b are x values, so we're picking an x value in between the x values a and b. And we're guaranteed by this theorem that there will be a y value f of c that is equal to n. So in other words, in the interval a to b, the open interval, there will be some x value that when you plug it in your function will give us back any random y value we want in between f of a and f of b. So in other words, what this is saying is the function has to hit every single y value that is in between f of a and f of b. In other words, the intermediate values between them. That's where the name of the theorem comes from. And it guarantees that some x value in between a and b will take on those y values. Now I think it's easiest to see with a visual. In this picture on the left, we've got f of a and f of b, those y values, and we're saying some random y value in between n. Well, our theorem guarantees that some x value will send us to that y value on the function. So basically, an x value in between a and b, when we plug it into our function, will give us back the y value that we desire. The picture on the left shows that it happens once, and the theorem guarantees that it happens at least once. The picture on the right shows that if we pick a certain y value, it might occur more than once, as in the picture on the right. Another way to think of it is the function, because it's continuous, can't just jump over a y value. So say if f of a was 1 and f of b was 5, that means our function in between a and b, the x values a and b, must hit every y value in between 1 and 5. Now it's very important that the function needs to be continuous for this. If the function is not continuous, then we've seen lots of things where it could jump over a bunch of y values. So the theorem only works for continuous functions. Now, an important application of this theorem is when finding roots. We're going to show with the intermediate value theorem that there is a root between 1 and 2. What we'll do is we'll first plug in 1. So we'll find f of 1. So we'll have 4 times 1 cubed minus 6 times 1 squared plus 3 times 1 minus 2. 1 cubed is 1 times 4 is 4. 1 squared is 1 times negative 6 is negative 6. 3 times 1 is 3. And then we'll have minus 2. This is really a positive 7 minus 8, so f of 1 will equal negative 1. We'll now do the same thing for 2, so we'll find f of 2. So we'll have negative 4 times 2 cubed, minus 6 times 2 squared, plus 3 times 2 minus 2. Well, 2 cubed is 8. 2 cubed is 8. 8 times 4 is 32. 2 squared is 4. 4 times negative 6 is 4. 3 times 2 is 6. And we'll have a minus 2. So this is really positive 38 minus 26. So that'll give us a positive 12. So this is where the intermediate value theorem comes in. We have a polynomial. We know polynomials are continuous everywhere. So that satisfies the continuous part. We've got a closed interval from 1 to 2. Okay, those being x values from 1 to 2. And we know f of a, our f of 1, is negative 1, and f of b, our f of 2, is 12. By the intermediate value theorem, we then know the function must take on every y value in between negative 1 and 12. Because 0 is in between there, that guarantees that there is a root. So we can say now by the intermediate value theorem, and we can abbreviate it IVT. Okay, and it's important, you need to say that that's why it works. By the intermediate value theorem, there must be some x value between 1 and 2 such that f of x equals 0. Okay, and again, the reason for that is because it must hit every y value in between negative 1 and 12. Now, if we wanted to get more specific, we could narrow it down some. So if we took, say, f of 1.2, we would find that it's negative 0.128, and f of 3, or f of 1.3, is positive 0.548. So again, by the intermediate value theorem, we know that there must be an x value between 1.2 and 1.3 that's going to take on 0, because 0 is in between our two y values. And you could narrow it down further if you wanted. This is what you get if you put in 1.22. That's what you get if you put in 1.23. So we could narrow it down that actually our root is between 1.22 and 1.23. And a long time ago, before they had calculators, that's one way that they could approximate roots of functions using this intermediate value theorem. So, kind of a result from the intermediate value theorem, if we have a continuous function that has no zeros on the interval, then we can assume that either the function is always positive or it's always negative. Because if it was both positive and negative, we know it must take on the values in between, which one of them would be 0 at some point. And it seems kind of an obvious result, but nonetheless, it's one that we get from the intermediate value theorem. So if there's no zeros in that interval, it must either be all positive or all negative. So because of that, we are going to see if we can find the intervals where this function is positive and negative. Well, we need to look for the roots and any vertical asymptotes. Those are the places where it could switch from positive to negative. You learned in pre-calc in your rational functions unit that the roots are determined from when the numerator is equal to 0. Since this can factor into x minus 2 and x minus 2, the only place we will have a root is at x equals 2. You also learned in pre-calc, and we've talked about this here, that when your denominator is 0 in a rational function, that's where your vertical asymptotes are. The function will not be defined there. So we can take our denominator and set it equal to 0. We will find that we have vertical asymptotes at positive 3 and at negative 1. So what we'll do is we'll put those values on a number line. We know at negative 1, at 2, and at 3, those are the spots where we could change from positive to negative. At the negative 1 and the 3, where our function's not defined, at 2, we know our function is 0. So those are the three cases where it's neither positive nor negative. What we'll do now is we'll test to see where it's positive and where it's negative. It's sometimes helpful to have the function in factored form when doing that. So we have x minus 2 times x minus 2 over x minus 3 times x plus 1. Okay, and again, that's just our numerator and denominator factored out. Let's pick something from this interval here, say like negative 2. All we care about are the positives and negatives. When you plug negative 2 into the top, you'll get a negative in both cases. When you plug a negative 2 in the bottom, we'll get a negative in both cases. So in both top and bottom, you'll have a negative times a negative, so you'll end up with a positive over a positive. A positive divided by a positive is a positive, so we know that section is positive. We can do the same analysis for the next section. An easy one would be 0. When we put 0 in both things in the numerator, we get negatives. In the denominator, we get a negative and a positive. So a negative times a negative is a positive. A negative times a positive is a negative. And then when you do a plus divided by a minus, you'll get a negative. Doing the same analysis with a 2.5 here. We'll get a plus and a plus in the numerator. We'll get a minus and a plus in the denominator. Positive times a positive is a positive. Negative times a positive is a negative. A positive over a negative will give us a negative. And lastly, if we pick something like 4 here, we'll get a positive, a positive, a positive, and a positive. Everything's positive, so that section will be positive. Now, the reason I didn't switch it to, you might remember back from pre-calc, that in the numerator, it's like we have x minus 2 being squared. And when you had an even multiplicity, so like squared to the 4th of a root, it ended up bouncing there. So really what's happening is our function's coming from underneath the x-axis, hitting the x-axis, and bouncing off and staying on that side. That's why it stays negative. So we need to tell what intervals is it positive and negative. We are positive when x is less than negative 1 or when x is greater than 3. And we are negative when x is between negative 1 and 2 or when x is between 2 and 3. Now, another way you could write that in interval notation, we could have said negative infinity, comma, negative 1, and the union of that with 3 to infinity. That would be our positives. For the negatives, we would say negative 1, comma, 2, the union of that with 2, comma, 3. Okay, when we get into looking more in depth at where functions are, say, increasing and decreasing, we'll look and see where things are concave up and concave down later in this year. We'll use the notation on the right more frequently. Okay, but for now, either of those is fine. So we're going to look at some more continuity on this video as well. We want to see if we're continuous at each of these values. So to start out, we're going to look at x equals 3. Remember, to be continuous, the limit must exist, and the value of your limit must equal the value of the function at that point. So let's first see if the limit exists at 3. So we'll look at as x approaches 3 from the left of f of x, and the limit as x approaches 3 from the right of f of x. Well, as x approaches 3 from the left, we'll be using this function. When we plug 3 into that function, we get back 10, because 3 plus 7 is 10. When x approaches 3 from the right, those will be values greater than 3, so we'll use that function. Well, a negative 3 plus 7 gives you 4. Absolute value of 4 is 4. Since the limit from the left is 10, the limit from the right is 4. Our limit as x approaches 3 of f of x, therefore does not exist. If the limit does not exist, it cannot be continuous there. So we are not continuous at x equals 3. Now we can do a similar process for 2, or negative 2, I should say. Let's first look at the limit as x approaches negative 2 from the left, and the limit as x approaches negative 2 from the right. When we approach it from the left, we'll use this function. Well, negative 2 squared is 4. 4 plus 1 would give us 5. When we approach from the right, we'll use the middle part. Negative 2 plus 7 also gives us 5. So we know our limit as x approaches negative 2 of f of x overall is equal to 5. So that's good. Now we need to see what is f of negative 2. If that is also equal to 5, it'll be continuous. If it's not equal to 5, we will not be continuous. Well, the negative 2 is in the top function, because that's where we would be equal to negative 2. And we already know when we plug that in, we get 5. The limit is equal to the actual value at negative 2, so we can say that it is continuous at x equals negative 2. Next, we're going to kind of review finding the slope of a secant line. A secant line crosses the function twice, so you should have 2 points. So for our slope, we'll just do change in y over change in x. The 2 points we're going to use, P, which is 4, 2. And they tell us Q is x comma square root of x. The reason that's the case is this is our function. We have x comma y, but we know y is just square root of x. So x comma whatever you get back when you do square root of your x value. They want us to use x equal to 3.99. So really the point of Q will be 3.99 comma whatever we get back when we do the square root of 3.99. Now you could punch that in your calculator and keep it out all the way, but it might be a little neater to just leave it as square root of 3.99. Now all we have to do is just do the slope. So we'll do our change in y over our change in x. So we can do square root of 3.99 minus 2 over 3.99 minus 4. And again, that's just change in y over change in x. And if we punch that in our calculators, we want it out to 6 decimal places, so we should get 0.250156. So basically, that's a pretty close estimate to what the slope of our tangent line is at 4. Okay, it's really close to it. It won't be quite exact, though. Similar to what we did 2 examples ago, we're going to see where's the function discontinuous. Well, let's look at each of the parts first. We have a square root of a negative x. Normally, square root of x would be continuous where it's defined, which would be on the positives and 0. But because we have a minus in there, it's really going to be defined on the negatives and 0. And because x is less than 0, it'll be defined in that whole section. 3 minus x is a line. That's continuous on all real numbers, so we're good there. And we have a quadratic down in the bottom one that is also continuous on all real numbers. So each part individually is a continuous function. We need to look at where it changes from one function to the next. So we'll start out, we'll look at our limit as x approaches 0 from the left of f of x, and our limit as x approaches 0 from the right of f of x. As x approaches 0 from the left, we would be coming from negative numbers, so that would be this function. When we plug 0 in, we would get back 0. When we come from the right, we would be using this function. When we plug 0 in, we'd get back 3. So therefore, the limit as x approaches 0 overall of f of x does not exist because the left-hand limit does not equal the right-hand limit. So therefore, we can say f of x is, you can either say not continuous or discontinuous. They mean the same thing. At x equals 0. So we found one discontinuity. Let's test the other one. We'll do our limit as x approaches 3 from the left of f of x. And we'll do our limit as x approaches 3 from the right of f of x. From the left, we'll be using this function here. When we plug in 3, we get back 0. From the right, we'll be using this function here. When we plug in 3, 3 minus 3 is 0. 0 squared is 0. Left-hand limit equals the right-hand limit. So our overall limit equals 0. Now we need to check and see what is f of 0. If that also equals 0, then we're continuous. If it doesn't, then we're not continuous. 0 is defined in this function here, because that's where we have the equal to. Oh, sorry, we're not testing 0, we're testing 3. Let me change that. We're doing x approaches 3, so we want to find f of 3. So it's not this one, we're equal to in this one. So when we plug in 3 here, we know 3 minus 3 is 0. 0 squared is 0. Therefore, our limit and our function are both 0, so we can say it is continuous. But I guess based on how the question's worded, they just want to know where it's discontinuous, and we found that already over on the other side. So it is only discontinuous at x equals 0. In this picture, we want to find if x equals 5 is continuous from the right, left, or neither in this picture. Now, in case it's hard to see, there's a closed circle there, an open circle here. We've got a hole there. Comes to a corner point there. You've got a hole there with a closed circle. We've got an asymptote going on at 5. We got open here, closed there, open, open. So at 5, remember it's continuous from the left if your function's limit from the left takes on the value at that x value, so at 5. Because 5 is not defined, when x equals 5, our function has an asymptote, it cannot be continuous from the left or continuous from the right. So this would be a neither. An example of continuous from the right would be at x equals 6. Because as we come from the right, the closed circle is with the right-hand part. An example from continuous from the left would be at -5, because the closed circle is with the part as you come from the left. But the question wanted to know at x equals 5, because x equals 5 is not defined, it can't possibly be continuous from the left or from the right. So we're going to see if we can find a limit of this function that has an absolute value in it. We need to redefine absolute value of 2 minus x. If you have x values that are less than or equal to 2, so if you have things like 2, 1, 0, -1, -2, and so forth, when you plug those in for x, you get a positive inside the absolute value. Because you get positives inside the absolute value, when you take the absolute value, it doesn't change anything. So when x's are less than or equal to 2, you just get whatever 2 minus x is. However, when x is greater than 2, so values like 3, 4, 5, whatever you get back, it's negated. So what will really happen is whatever 2 minus x ends up being, it gets negated. When you distribute that negative, that ends up as negative 2 plus x. And we've seen something like this looking at just plain old absolute value of x before. We can redefine it so that we have it without the absolute value bars, and then it makes it easier to evaluate. So if we want to look at the limit as x approaches 2 from the left, and the limit as x approaches 2 from the right, we will use our redefined way of writing absolute value of 2 minus x when doing this. When we want to look at 2 from the left, we will really use the top part to replace absolute value of 2 minus x. So really we'll have 2 minus x over 2 minus x for our function. And actually I should rewrite that as that's really the limit as x approaches 2 from the left of 2 minus x over 2 minus x. Well, because that's the same thing, both top and bottom, anything divided by itself is just 1. So it's always going to be 1. Now for the other one, the limit as x approaches 2 from the right, we'll write f of x as 2 minus x over, and because we have values that are greater than 2, we'll rewrite the bottom as negative 2 plus x. Well, this is the same as saying the limit as x approaches 2 from the right is 2 minus x over a negative 2 minus x. So if we pulled the negative 1 out, well, you have 2 minus x on top, 2 minus x on bottom. Those divide out to 1. You had a negative on the bottom, so that really just becomes negative 1. So your limit of the function from the left is 1. Your limit of the function from the right is negative 1. So therefore, our overall limit, the limit as x approaches 2 of 2 minus x over the absolute value of 2 minus x does not exist, because the limit from the left does not equal the limit from the right. That's all for today's video. See you next class, period.